In section 11.1, let's review functions. What is a function? A function is a machine where we enter an input, let's say x, and we get an output, and we'll call this output f of x. The set of input values is called the domain of the function, and the set of output values is called the range. The domain is all of the possible inputs or x values for our function, and the outputs, those are our y values of the function, or f of x values. In example 1, let's determine whether the set of ordered pairs is a function. If it is a function, state the domain and range. Well, what is a function? Well, a function takes one input and you get exactly one output. One input gives us exactly, the keyword here is exactly, one output that corresponds to it. So let's look at question A. We have the ordered pair, -3, 9, 2, 5, 3, 6, 7, 9. What's happening is -3 gets sent to 9, a 2 gets sent to a 5, a 3 gets sent to a 6, and this 7 here gets sent to a 9. Is this a function? We can look at each one of these, and each input, which is the x values, each of these x values has exactly one output. -3 goes to one number 9, 2 goes to one number 5, 3 goes to one number 6, and 7 goes to one number 9. So this is definitely a function. Think about the vending machine. You can go buy a soda at the vending machine, but your friend can also buy the same soda, so this is a function. It's an okay situation. What is our domain? Our domain is the set of all these x values, which is -3, 2, 3, and 7. The range is the set of the y values. All of these y values is going to be our range. So we'll enter the range. We have 5 as a possible output, 6, and 9 as a possible output. We only mentioned the 9 once for the range. In this example, we have 1 gets sent to 2, 3 gets sent to 5, and the 1 also gets sent to a 9, and -9 gets sent to a 0. Is this a function? It is not a function. Why is this not a function? This is a situation where the number 1 has two outputs. It has an output of 2 and an output of 9, so this is not a function. This is a scenario where you enter $1 into the vending machine and you get two different outputs, and that cannot happen. This is not a function. Let's look at part C. The -6 goes to a 5. The -3 goes to a 5. The 0 goes to a 5. 3 goes to 5. And even 6 goes to that 5. Is this a function? Yes, this is a function. This is a function because each of these values, -6, -3, 0, 3, and 6, go to exactly one output. So this is a function. This is a situation where every single person bought the same item, and that's possible for that vending machine. This is possible. This is a function. What is the domain of this function? Well, it's all of the x values. That's -6, -3, 0, 3, and 6. What is our range? A range, well, there was only one possible output, and that's a 5. So our range is just 5. In part D, let's determine if this is a function. Let's draw a picture out. It seems that every single number gets sent to a unique number so far. But if you look at the last one, we have a 10 also getting sent to a 1. So this is not a function. It fails at the very end. This is not a function because the 10 has two different outputs, that -1 and that 1. So this is not a function. Let's look at the vertical line test. If a vertical line can be drawn that intersects a graph at more than one point, the graph does not represent a function. Let's look at our previous example, part D. This was not a function because if you notice, we have an x-coordinate that goes to a number and the same x-coordinate going to a different number. These are 2 points that actually lie directly on top of each other. Right? They lie on top of one another. So we can see that if we draw a vertical line between the 2 points, they would pass more than once on the graph. So that's what the vertical line test basically says. If we can intersect the graph at more than one point with any vertical line, it fails as a function. So let's look at example A. Is this a function? If I draw vertical lines, I will never intersect this more than once. This automatically is considered a function. In part B, every single vertical line has to intersect only once to be a function, but we have a problem. I can pass through this line 3 times, which disqualifies this as a function. So it's not a function. We're able to pass through it more than once. This is not a function. Same thing for part D. Actually, part C. We can pass through this twice. So this is not a function. This is not a function. In part D, this is a function. No matter how many vertical lines I do, we will never cross the graph more than once. So this passes the test. This cannot intersect more than once. It is a function. Let's evaluate functions. This is using function notation. So in part 1, we have f of x equals 3x plus 4. Find f of -8. This -8 is our input. We're going to substitute x equals -8 into the original equation. Now to do this, you start by writing f of -8, put an equal sign, and then you can start your work. So this is what we're evaluating. We're plugging in a -8 into the x. And when you do this, you want to make sure you use parentheses. This is 3 times -8, which is -24, plus 4. We can add that, and that gives me a -20. And that's it. Stop right here. Notice when I do my work, I line up my equal signs, and I just write f of -8 one time, and that's it. You don't want to write it more than once. This is the proper way to present our work. In example 2, we want to find f of 9/2. So again, I'll start by writing f of 9/2. That's what we want to find out. And then we'll replace the x here with a 9 over 2. So this is 6 times 9 over 2. Using substitution, put a parenthesis around that, 9 over 2. Put an equal sign below the previous equal sign, and then we can reduce. You can see here the 2 reduces to a 1, the 6 reduces to a 3, then we can multiply 3 times 9. And that gives us 27 minus 11. And we can simplify that as 16. And that is our solution. F of 9 over 2 is equal to 16. Let's look at example 3. F of x equals negative 3/4 x plus 15. Let's find f of negative 12. Again, that negative 12 is the input. That's what we're plugging into the function and getting an output. F of negative 12 equals negative 3/4 times 12 plus 15. Let's reduce this fraction. We'll reduce this 4 to a 1, and this 12 reduces to a 3. And so we can simplify this as negative 9 plus 15, which we can simplify our final answer as 6. So that's it. Our solution is f of negative 12 equals 6. Let's look at example 4 now. This is f of a plus 8. So we want to plug in this entire expression. We want to use a plus 8 as the input. So we'll write f of a plus 8 first. Then I will substitute a plus 8 with parentheses into my function. Now this means I got to distribute. So let's distribute the 5. This is 5a plus 40 minus 8. We can simplify this a bit. This is 5a plus, and 40 minus 8, that's going to give us 32. And we stop here. This is it. 5a plus 32. I cannot simplify that any further. We're going to leave this problem alone. This is it. In part 5, same situation. Let's try to substitute 6n plus 5 as our input. We write f of 6n plus 5 equals negative 3 times 6n plus 5 minus 16. And again, we'll have to learn how to distribute here, so we're going to distribute at negative 3. Negative 3 times 6n gives me negative 18n. Negative 3 times 5, that's a negative 15. And we'll bring down that negative 16. Let's collect like terms. Write down the negative 18n. Negative 15 minus 16, that is a negative 31. And that's it. We can't simplify this anymore. We have to stop right here. This is a good solution. In example 6, let's find f of negative 7. This is our input, but there's two x's. So that means you got to plug it into two different locations. Let's try that. F of negative 7 written down first. Then you'll plug in a negative 7, square it. Plug in a negative 7 again for the x, and bring down the 16. Now we'll simplify this expression. We have negative 7 squared is a positive 49. Negative 9 times negative 7, that's a positive 63. And don't forget that positive 16 on the right. So let's add up all these numbers. We have 49 plus 63 plus 16. That gives me 128. This is our final result. In question 7, we have f of x plus h. That's what we need to use as the input to my expression. Now, there's two locations that we have to plug that in. So we'll write f of x plus h first. Then we'll plug it in for the first x. And we'll plug it in again for the second x. That means I have to FOIL x plus h. So we'll multiply it to itself twice. And this x plus h here, we can actually get rid of the parentheses. So we'll say that's x plus h. We'll have to FOIL now. X times x is x squared. X times h, well, that's x times h. H times x is also x times h. Just write it backwards. And h times h gives us h squared. And don't forget to bring down the x plus the h. We can simplify this. This is x squared plus these two can be added as 2xh. H squared comes down, x comes down, and h comes down. That's it. We can't simplify anymore. I can't add any variables together because they're not like variables. Determine the domain and range of the function on the graph. Also determine the x and y intercepts if they exist. Now remember, the domain was the set of all x values. So if you look at the graph, this graph extends forever towards the left and forever towards the right. That's what I'm going to use to determine the domain. So it goes forever to the left and forever to the right. So it has all possible x values. So the domain is negative infinity to infinity. Now the range is the y component. So I'm going to look how far the graph goes down for the y component to how far it goes up. It stops down here at, it looks like -1. So I'm going to say it starts at -1 with a square bracket because it actually includes that for the y coordinate. And it goes up forever. So we have a range that goes from -1 to infinity. And again, don't forget infinities always have parenthesis symbols. The problem also wants us to find the x-intercept. Well, we have 2 here. There's 2 x-intercepts. Let's call them 2, 0, and we'll call the other one 4, 0. What is the y-intercept? Well, that's where it crosses the y-axis, and it looks like, according to this picture, it looks like the y-intercept is the point 0, 8. In example 2, again, I want to start with the domain. I ask myself, how far does it go left to how far does it go right? Well, if you look at the scale on the x-axis, you're going to have to go on forever in either direction to see this whole graph. So the domain, again, is negative infinity to infinity. For the range, we ask how far down does it go to how far up. So it goes down, if you were on an elevator, down only up to here, which is a positive 4. So we're going to go down to 4 with a square bracket, and if we look at the picture, it goes up forever. We have to go up on this elevator forever. So the range is 4 to infinity. Now, what is our x-intercept? Well, we don't have any. It doesn't cross the x-intercept at all, so the x-intercept, well, we'll say there's none. What is the y-intercept? That's where it crosses, and it looks like it crosses at the point 0, 6. Let's look at the domain for this graph. If I were on the x-axis, I would drive up to here to see the entire picture, which means my range, or actually my domain goes from -4 all the way to infinity because it goes forever towards the right. This is infinity. What is my range? Well, how far does it go down? Well, it goes down to, for the y-axis, it goes down to 2. And it has a slight rise, and that rise is going to be forever, so the range goes up forever. So it's square bracket 2, comma, infinity. Let's try it again. The domain, again, I'm driving on that x-axis. How far do I have to drive to see the whole graph? Forever to the left. If I go on the x-axis, how far do I have to go? Well, I can stop right here at -1. So the domain is negative infinity to -1 with a square bracket. What is the range? Well, the graph, it has a decrease. It goes down forever. So we have to go down forever to see this picture. It has a very slow decrease, but it's going to keep going forever down. So that's negative infinity. And if we go up, we have to stop right here at a square bracket 2. So the range is negative infinity, comma 2. Again, you do not use square brackets for infinities. You only use it for values that are included. So the 2 is included, but infinity, we can't really include that as part of our interval. It says, use the graph to find the indicated function value. So I'm going to give you some questions here for this example. Let's suppose I asked you to find f of 0. Well, f of 0 basically means the x coordinate is 0, and I want you to find the output. The output is the y coordinate. So I gave you the 0 as the x coordinate, and if you look at the graph, this is the point 0, 7. This is my input x, this is my output y. So f of 0 is 7. That's the output. That's how function notation works. So we could test it again for this point here. What's f of -7? Well, that's the x. This is the point -7, 0. So this means f of -7, that output is 0. So this again is my input, the x coordinate, and the y coordinate is the output. Let's try it again for this example. I want you to do it on your own. Let's have you find f of 0. And we'll also let you find f of -6. And we'll do one more just for fun. Let's find f of -2. So take some time. Try this out on your own. For number 1, f of 0, the x coordinate is going to be 0. So that's the point 0, -9 on the graph. So f of 0 is -9. F of -6, we'll have to look for the x coordinate of -6, something. And this is -6, 0. So f of -6 is 0. What's f of -2? Well, we'll look at the x coordinate. I want to figure out where it touches the graph. And this looks like this is the point -2, -10. And so I can say f of -2 is equal to -10. Again, this is my x, or my input, and this is my y, or the output. Use the graph to find the value of x that will satisfy the given equation. So in this example, I want to see if we can go backwards. let's suppose I said f of x is equal to -4, and I want you to solve for x. Well, how would you do it based on the picture? Well, this is the y coordinate, and I'm looking for the input. So if you look at the graph, this point has the ordered pair 5, -4. So that means x has to be equal to 5, because f of 5 would equal -4. And that's what we're doing in this problem. I am giving you the output, or the y coordinate, and asking you to find the x that would work. So this is backwards. Let's look at another example. Let's suppose f of x was equal to, let's say, 5. What x values would work? Well, in this case, if I go to 5, it looks like the graph crosses at 2 different locations, and this corresponds to 2 different x values. So in this case, x could be equal to 2, or x could be equal to 8, because the point 2, 5 and 8, 5 are on the graph. And so we have 2 different solutions for x. Let's try it again. Let's look at example 2. I want you to find f of an x that would give us -2. And so think about it for a moment. If we look at the graph, this is the point 5, -2. So what x value would work? Well, this means f of 5 equals -2. So that missing x right here must be equal to a 5. Let's look at the last example here. Let's suppose f of x equals -5. I want you to solve for x using the picture. Now, to do this, you look for the y coordinate of -5 and where it crosses your graph. So we have 2 points here. Got the point 1, -5, and this point looks like 7, -5. That means we have 2 solutions. X could be equal to 1. X could be equal to 1. Or x could be equal to a +7, because this is our input x. We are given the output is a -5 or y, and so we're asking you to find x.